Why are irreversible processes important for understanding entropy? Imagine watching a glass fall and shatter on the floor. The pieces scatter everywhere, and the mess is impossible to put back together perfectly. This simple event shows us something about how energy and disorder work in the universe. When we talk about entropy, we are talking about how disorganized or random a system is. But why do some processes happen naturally and can't be reversed? That's where irreversible processes come into play. They are key to understanding why entropy always tends to increase in real-world systems. In thermodynamics, entropy measures how many ways the tiny parts of a system can be arranged without changing its overall state. Think of it like a deck of cards. The more shuffled it is, the higher its entropy. Reversible processes are like carefully sorting the cards back into order, an ideal situation where no entropy changes happen. But in real life, most processes are irreversible. For example, when you heat a cup of coffee, the heat spreads out into the room. You can unheat the coffee and gather all the heat back into the cup. This spreading out is an irreversible process. Irreversible processes are important because they show us how energy is lost in real systems. When energy moves or transforms, some of it turns into heat that can't be used to do work anymore. This is why engines and machines are never 100% efficient. Friction, turbulence, and other effects cause energy to dissipate, increasing the total entropy. This increase in entropy means the system becomes more disordered and less capable of doing useful work. Understanding these processes helps engineers design better systems. They try to minimize the amount of energy lost as heat and reduce entropy generation. For example, in engines, reducing friction and optimizing heat transfer can make the system more efficient. It also explains why certain natural processes only go one way. Once entropy increases, it's statistically unlikely to decrease again without outside intervention. The second law of thermodynamics states that, in an isolated system, entropy can stay the same or increase but never decrease. So, by studying irreversible processes, we see how energy naturally flows and spreads out. It helps us understand why energy quality declines over time and why systems tend to move toward disorder. This understanding is essential for designing efficient machines and for grasping the fundamental behavior of energy in our universe.